in exactly 48 hours, at 6 minutes past midnight, Coordinated Universal Time. An object that has been journeying for 7 billion years through the void between stars will reach the closest point it will ever come to our planet. At this exact moment, 23 nations on Earth will activate the largest planetary defense drill in recorded history. A coordinated effort that spans continents and space agencies. Take a moment to grasp this. The timing is so precise, so perfectly aligned, that if it were written into a science fiction novel, an editor would likely deem it too convenient to be believable. But this isn't fiction, it's December 17th. Liantianling Arshawu, and the interstellar visitor, known as 3I, Atlas, is now closer to your living room than it has ever been to any world in our solar system. An unprecedented opportunity for humanity to study an interstellar object in detail. What transpires in the next 72 hours may forever alter our understanding of our place in the universe, the objects that drift between the stars, and the silent preparations that have been underway by global powers while most of us were unaware. Before we dive into what's unfolding above us at this very moment, be sure to like and subscribe to stay updated with the latest cosmic revelations. Now, let's begin this incredible journey. So, what is happening in the sky above you right now, 3I? Atlas is currently 269 million kilometers away from Earth, roughly 8 times the distance between our planet and the Sun. While that sounds vast by human standards, in cosmic terms, this object is practically at our doorstep. This is the closest any confirmed interstellar object has ever come to Earth during a period when we have the technology to study it properly. The first interstellar visitor, Oumuamua, caught us completely off guard in 2017. By the time we recognized it, it was already racing away, leaving nothing but mystery and debate. The second, Dvi Borisov, behaved more like a conventional comet, offering fewer enigmas but also fewer chances to study it. But 3I, Atlas, is different. It arrived with enough warning for us to direct every major telescope on Earth and in space directly at it, providing a rare chance for detailed observations. Hubble has been watching. The James Webb Space Telescope has been watching. The European Space Agency turned its XMM Newton X-ray Observatory toward this object for 20 straight hours. Mars orbiters captured images as it zoomed past the red planet at 19 million miles. Even spacecraft on their way to Jupiter have redirected their instruments to gather data before this cosmic traveler disappears forever into the darkness of space. And here's where things take a strange turn. On November 27th, 2025, just 3 weeks before its closest approach, the International Asteroid Warning Network activated what officials are calling the largest planetary defense exercise ever conducted. This isn't just a simulation running on computers in some secret lab. This is a real, live, global operation involving multiple space agencies, with data streaming in from observatories and spacecraft around the world. This exercise isn't just about tracking the object. The purpose is to test how quickly humanity can detect, track, and respond to a high-velocity, near-Earth object. The object they're using for this test is 3I, Atlas. Now, let's be clear, every major space agency has stated that 3I, Atlas, poses no threat to Earth. It will pass at nearly twice the distance between the Earth and the Sun, with no trajectory bringing it close to impact. The planetary defense drill is described as an exercise of opportunity, an invaluable chance to test global response systems on a real, moving target. While this explanation makes sense, the scale of the operation raises some interesting questions. The European Space Agency recently secured a record €1 billion budget, a significant portion of which is allocated to space resilience initiatives, including planetary defense. They've even referenced the 2029 flyby of asteroid Apophis as a key motivator for these preparations. These drills include simulations of deflection missions, civil defense protocols, and communication strategies for public outreach. But what exactly does one communicate during a planetary defense scenario? Why does it require international coordination to practice, while there is no immediate threat from 3I, Atlas? There's something about the scale of these preparations that feels out of proportion for an object that we're told is harmless. The official narrative is clear, 3I, Atlas poses no danger. But the sheer intensity of this global response suggests that something more is at play. The reality is that while the immediate threat is nil, the preparations may be about future objects that are more dangerous and much closer. When 23 nations activate their space defense infrastructure around an object that is supposedly harmless, you have to ask, what else might they be testing? What capabilities might they be enhancing for the next threat? Now, let's consider the trajectory of 3I, Atlas. It entered our solar system from the direction of Sagittarius, near the galactic center. It has been traveling through interstellar space for over 7 billion years, well before Earth itself existed. As it neared our Sun, it began accelerating at speeds exceeding 246 kilometers per hour. This is the fastest any object of its kind has ever been clocked in our solar system. Once it passes our Sun, 3I, Atlas, will head back toward the stars, carrying with it the secrets of its distant birthplace, a star system that may no longer exist. But this close approach is our only opportunity. After December 19th, it will begin to fade from view as it accelerates away from us, leaving us with only the data we collect now. In just a few months, even our most powerful telescopes will struggle to detect it. This is not an object we can revisit. This is a fleeting opportunity, a moment that will be lost forever if we fail to capture it. With its incredible velocity, no spacecraft can catch up with it. Our window of observation is closing in just 72 hours. If you were a planetary defense official, knowing that future close encounters with hazardous objects are likely, wouldn't you seize this chance to test every system, to measure the readiness of every sensor, and to evaluate the efficiency of your communication protocols? The generous interpretation is simple. The global response to 3I, Atlas, is a well-planned, competent exercise to prepare for future threats. But there's another, more unsettling interpretation. What are they preparing for? Could the scale of this operation be testing for something far more dangerous? Could there be unknown variables hidden in the behavior of 3I, Atlas, that they're not revealing? 3I, Atlas will pass closest to Earth on December 19th at 6:02 a.m. UTC. As it crosses this milestone, a wave of data will flood in, analyzed by scientists around the world. In that data may lie answers to questions we haven't even thought to ask yet. But what's even stranger is that 3I Atlas is not behaving like a typical comet. It is displaying anomalies that have baffled researchers since the first images were captured in July. The most striking of these anomalies is the structure extending from the nucleus of the comet, pointing directly at the Sun. This structure now stretches further than the distance between Earth and the Moon. An unprecedented observation. This discovery was quietly noted in a minor bulletin from the Minor Planet Center document MEC 2025 U142, which detailed the activation of the International Asteroid Warning Network's Comet Astrometry campaign, with 3I, Atlas, as its centerpiece. The IAWN, operating under the United Nations, is responsible for coordinating the global response to Earthbound objects. This is the first time the IAWN has centered a campaign on an interstellar object. They are testing their systems against an object traveling at 60 kilometers per second, a speed that defies our models and challenges our understanding of how these objects behave. Agencies from around the world, NASA, the European Space Agency, JAXA, ISRO, and CNSA, are all contributing to this unprecedented effort. More than 80 observatories worldwide are participating. With a record 171 attendees at the kickoff meeting in October, this is not just a drill, this is a real-time, coordinated response to a once-in-a-lifetime event that might reveal much more than we expect. JAXA, the Japanese Space Agency, has contributed its advanced space situational awareness systems, gathering valuable data on 3I, Atlas, as it traverses the solar system. The Indian Space Research Organisation ISRO is also deeply involved, providing its own tracking and detection capabilities to help refine the object's trajectory and assess its potential risk. Remarkably, even the China National Space Administration, which is traditionally cautious about sharing real-time data with Western agencies, has joined this collaborative effort, contributing valuable insights into this interstellar visitors movement. This is not a small endeavor. Australia, Canada, Israel, South Korea, and more than a dozen European nations have enrolled their observatories and research institutions in the Global Observation Campaign. Over 80 individual observers from around the world have formally signed up, each contributing data to a unified tracking network. The initial kickoff meeting in October brought together 171 participants, setting a new record for any IWN campaign. The mid-campaign teleconference held on December 9th saw over 100 experts and scientists participating in real-time discussions, all focused on a single object racing through space at a speed that challenges our conventional understanding of velocity. But the real question is, what exactly are they practicing for? According to the official statements, the primary goal is to test the ability of the observing community to extract precise astrometry from comet observations. Astrometry is the science of measuring an object's position in the sky with extreme accuracy. While this sounds highly technical, it is critical for planetary defense. If we cannot precisely determine where an object is at this very moment, we cannot predict where it will be in the future. And if we can't predict that, we can't assess whether it poses a threat. For asteroids, this kind of calculation is relatively straightforward. They are solid, their surfaces are stable, and their brightness comes from sunlight reflecting off the rocky surface. But comets, like 3I, Atlas, present a far more complex challenge. Comets are not solid bodies. They are surrounded by a large cloud of gas and dust called a coma. And this coma can significantly distort the apparent location of the nucleus. The fuzzy glow of the coma can pull measurements away from the actual center of mass, leading to errors that affect the entire trajectory calculation. 3I, Atlas, takes this problem to an extreme level. Its coma is massive, extending hundreds of thousands of kilometers in multiple directions, creating a distorted image that is far from conventional. It also displays an anti-tail, a structure pointing directly toward the sun that should not exist according to conventional physics. On top of this, the comet's surface is erupting with jets that create asymmetric brightness patterns, adding to the challenge. To make matters even more difficult, it's moving faster than any other comet humanity has ever tracked. This means that even the slightest errors in its position could lead to substantial errors in predicting its future trajectory. If the IWN wanted to stress test their tracking capabilities, they could not have selected a better object. But the exercise goes beyond just astrometry. Documents and statements from participating agencies reveal that this campaign is also testing orbital prediction drills, with teams working to refine their trajectory estimates as new data is continuously collected. Anomaly response protocols are also being tested, simulating what would happen if the object's behavior deviated from expected patterns. This is about practicing how quickly teams can respond when things go wrong. Moreover, the campaign includes multi-agency coordination exercises to see how swiftly NASA, ESA, JAXA, and their counterparts can exchange information, issue alerts, and make joint decisions in times of high uncertainty. Perhaps most intriguing, though, is the public communication aspect, specifically focused on combating misinformation and ensuring psychological preparedness. Why, you might ask? Would a planetary defense exercise need to focus on managing public communication? The most obvious answer is that a real threat scenario would generate immense public interest. And clear, consistent communication would be crucial to avoid panic. But the inclusion of misinformation management hints at something more specific. It suggests that officials are anticipating the spread of rumors and false claims, such as those that have already surrounded 3I, Atlas, from alien spacecraft theories to speculative trajectory changes. The focus on managing competing narratives shows a deeper awareness of the challenges in maintaining public trust during such a high-stakes event. The timing of these preparations is no accident. The European Space Agency ESA has openly referenced the 2029 flyby of the asteroid Apophis as a key motivation for accelerating their planetary defense capabilities. Apophis, a dry 170-meter asteroid, will pass within 31,000 kilometers of Earth on April 13th, 2029, closer than the orbits of our geostationary satellites. This will be a highly visible event, with Apophis crossing the sky over Europe and Africa. ESA officials have publicly acknowledged that the world will be watching when Apophis passes, and public interest in planetary defense will be at an all-time high. The 3I Atlas campaign is, in part, a rehearsal for that much more dangerous moment. However, Apophis is a known entity. Its orbit is well documented and its probability of impact is effectively zero. 3 Atlas, on the other hand, presents a different challenge. It tests our ability to respond to an object that arrives without warning, from a direction we weren't monitoring, and at a speed that compresses our response time to almost nothing. When 3I Atlas was first identified on July 1st, Liantianling Arshawu, the object was already within the solar system, and by the time its discovery was made public, there were only 4 months left before it would reach perihelion. This rapid timeline made it impossible to prepare for an intercept mission. A study conducted shortly after the object's discovery showed that reaching 3I Atlas with a spacecraft would require a delta V of at least 24 kilometers per second, far beyond the capabilities of any propulsion system currently in existence. If 3I Atlas had been on a collision course with Earth, humanity would have had no means of deflecting it. The only option would have been to observe its passage, helpless to stop it. This is the reality that planetary defense officials do not often discuss publicly, the scenario where detection comes too late. The object is too fast, and all of our preparations amount to nothing but documentation of an extinction event. The 3I Atlas campaign is not just about tracking comets, it's about understanding the limitations of our current defense capabilities. It's about identifying gaps in our detection systems and building toward a future where objects like this do not catch us by surprise. To that end, the European Space Agency has deployed 2 new systems that are central to Global Early Warning Strategy, MeerKAT, a ground-based detection network designed to scan large areas of the sky for faint, fast-moving objects, and Aegis, a space-based system that will eventually provide continuous coverage of areas that ground telescopes cannot monitor. These systems are still in the early stages of development, but the 3I Atlas campaign is providing real-world data to calibrate their performance. Every observation of 3I Atlas is teaching us something valuable about how to detect future interstellar visitors. Statistical models suggest that there are approximately 10,000 interstellar objects passing through our solar system at any given moment. But we have only detected 3. The Vera Rubin Observatory, the most powerful survey telescope ever built, is set to begin operations soon, and it's expected to discover an interstellar object on average every year. Within a decade, we may have dozens of these objects catalogued, each one providing valuable data to refine our understanding of what drifts between the stars. The current drill will continue through January 27th, 2026, 2 full months of continuous observation, coordination, and analysis. By the time it concludes, 3I Atlas will be on its way out of the inner solar system. But the lessons learned will continue to shape planetary defense for years to come. The relationships forged between agencies will remain, and the protocols tested will become standard operating procedures. What's important to remember here is that the 3I Atlas campaign is not about the object itself. It's about preparing for the next one. The next interstellar object may arrive from a different direction, at a different speed, and with a trajectory we can't predict. The only certainty is that it will come. The decisions we make when that moment arrives will depend entirely on the capabilities we have built and the lessons we have learned in preparation. Right now, as you read this, more than 80 observatories around the world are focusing on the same patch of sky, gathering critical data that will inform how we handle the next cosmic visitor. The next interstellar visitor may come from a completely different direction, traveling at a distinct speed and on a different trajectory. It could give us years of warning, or it might only provide us with weeks to prepare. The only certainty, however, is that it will come, and when it does, our ability to respond will depend entirely on the capabilities we've developed and the lessons we've learned in handling objects like 3I, Atlas. At this very moment, more than 80 observatories around the globe are observing the same patch of sky, gathering crucial data as this mysterious object hurtles through the cosmos. Spacecraft positioned around Earth, Mars, and en route to Jupiter are all collecting valuable data, aiming to track the object's every movement with precision. Simultaneously, government officials from 24 countries are working together in coordination calls, ensuring a synchronized effort to monitor the interstellar visitor that has been traveling for 7 billion years and is now reaching its closest approach to Earth. It is a remarkable convergence of international cooperation that exemplifies how much we have advanced in space observation. The official explanation for this massive undertaking is that it's simply routine, a valuable opportunity to practice planetary defense measures. While this may very well be true, there's something undeniably peculiar about 3I, Atlas, that demands further scrutiny. Since the first images were captured, it has presented baffling features that challenge our understanding of comet behavior. These anomalies raise questions that have not been adequately addressed by official statements or press conferences. One of the most puzzling aspects of 3I, Atlas, is the structure pointing directly at the Sun, growing larger with every passing day. The most recent observations reveal that it now extends further than the distance between Earth and the Moon. This phenomenon, which defies all known laws of physics, is referred to as the anti-tail. Typically, when you observe a comet through a telescope, the tail points away from the Sun, pushed outward by solar radiation and the solar wind's charged particles. This is not just a theory or a tendency. It's a fundamental principle of physics. When photons strike a comet's surface, they transfer momentum to the tiny dust particles and gas molecules, propelling them away from the Sun. This creates the familiar glowing tails we see in cometary images. It's a universal rule: every comet's tail points away from the Sun. Yet, 3I, Atlas, has a tail that points directly toward the Sun. Take a moment to grasp that an object traversing our solar system is displaying a structure that runs counter to everything we know about comet behavior. It's not just a rare occurrence or a slight anomaly. It is a large feature that has been observed throughout its entire journey. As of December 15th, the anti-tail of 3I, Atlas, extends roughly 500,000 kilometers from its nucleus in the direction of the Sun. That's greater than the average distance between Earth and the Moon. This feature is visible in amateur photographs taken with backyard telescopes and has been present in every image since Hubble first captured it in July. It has persisted through perihelion, the closest approach to the Sun, and continues to be visible as the comet moves outward on its outbound journey. Initially, researchers speculated that the anti-tail might be a perspective effect, an optical illusion created by the comet's position relative to Earth's viewing angle. Such an explanation might have worked for some solar system comets that display brief anti-tail features when the viewing geometry aligns perfectly. But 3I, Atlas, has been displaying this feature consistently for months, regardless of changes in the viewing angle. The anti-tail is not a fleeting effect, and it is not due to a shift in perspective. It's a real physical structure. The most recent images, captured by astronomers in Thailand and California in December 2025, show the anti-tail more clearly than ever. Using advanced techniques, such as the Larsen-Scanina filter, astronomers have been able to enhance subtle structures in cometary images. What they've revealed is a narrow, linear feature extending directly toward the Sun. It's not diffuse, like a typical comet coma, but rather, it has clear edges and structure almost as if it were deliberate. Now, it's important to approach this with caution. It's easy to read patterns into natural phenomena, to interpret what we expect to see rather than what's actually there. Comets are chaotic, unpredictable objects. They outgas in different directions, shedding material in jets that vary depending on the distribution of volatile ices beneath the surface. The anti-tail of 3I, Atlas could have a more mundane explanation that we haven't yet fully modeled or understood. However, the fact remains that no current model fully accounts for what we're observing. The anti-tail exists, and it has existed for months. It's growing, and it's still present despite changes in geometry, orientation, and position. No comet we've studied behaves in such a persistent and prominent manner. This is an anomaly that challenges our understanding. Harvard astrophysicist Avi Loeb, along with co-author Eric Cato, has published 3 peer-reviewed papers trying to explain this mysterious phenomenon. Their proposed mechanisms suggest that the anti-tail could consist of ice fragments ejected from the sun-facing side of 3I, Atlas. These fragments, being large enough to resist solar radiation pressure temporarily, would sublimate directly into gas, causing a cloud of evaporating ice particles to linger in the sunward direction instead of being pushed into the conventional tail. While plausible, this hypothesis requires very specific conditions. The ice fragments would need to be the right size, large enough to resist being pushed away by solar radiation, but small enough to sublimate quickly. The outgassing must be concentrated on the sun-facing side, and this process must continue for months to sustain the observed feature. No solar system comet has ever displayed this behavior so persistently or so obviously. Lowe's third paper, published in December 2025, offers an even more radical explanation. He suggests that the anti-tail might consist of objects that are not attached to 3I, Atlas at all, but are instead traveling alongside it in loose formation. According to this hypothesis, the comet is experiencing a slight acceleration away from the sun due to outgassing, and objects nearby, whether rocky fragments or smaller icy bodies, would lag behind, creating the appearance of an extension pointing toward the sun. If this theory holds, it would mean that 3I, Atlas, is not a single, solid object, but rather a collection of objects moving together through interstellar space. Lowe's papers don't go as far as to identify what these objects could be, maybe broken fragments from an ancient collision, or smaller bodies that formed alongside 3I, Atlas, billions of years ago, but whatever they are, their existence would challenge our assumptions about what drifts between the stars. More recent observations from amateur astronomers in Thailand and California show the anti-tail more clearly than ever. They've used specialized filters to enhance the subtle features of the comet's structure. What they've revealed is a narrow linear feature, visibly extending from the nucleus toward the sun. It's a feature with defined edges, almost as if it were deliberately formed. As fascinating as these observations are, we must still be cautious. It's easy to mistake patterns for intention, especially when we're dealing with chaotic, unpredictable objects like comets. The anti-tail of 3I, Atlas, may still turn out to have a conventional explanation, one that simply requires more advanced modeling techniques than we currently possess. But as of December 17th, Liansenling Arshawu, no published model can fully explain this phenomenon. The anti-tail is real. It has persisted for months, and it is growing larger. It should not be there, at least not according to our current understanding of physics. There's something fundamentally puzzling about the way this object behaves, and no one has yet offered a fully satisfying explanation. One recent paper reported that the anti-tail has been wobbling with a period of 74 hours, plus or minus 5 minutes. This wobble seems to track the orientation of the nucleus itself, suggesting that the anti-tail is somehow connected to the rotation of 3I, Atlas. If the jet producing the anti-tail is originating from a specific location on the comet's surface, a pocket of volatile material that only vents when facing the sun, then the rotation of the nucleus would cause that jet to sweep back and forth, almost like a lighthouse beam. While this explanation is somewhat reassuring from a conventional physics standpoint, it raises even more questions. Why is this outgassing so pronounced in the sunward direction? Why has it persisted for so long when similar features in other comets tend to be much more transient? And what is the composition of the material being ejected that allows it to resist the overwhelming pressure of solar radiation? The answer to these questions might lie in the composition of 3I, Atlas itself. The idea that the anti-tail is caused by localized outgassing rather than some exotic, unknown mechanism seems plausible at first. However, it introduces its own set of fascinating questions. Why is the outgassing so prominent in the sunward direction? Why has it persisted for so long? Unlike similar features seen in comets from our solar system, which are typically transient, and perhaps most intriguingly, what is the nature of the material being ejected that allows it to resist the immense pressure from solar radiation? These questions point to the possibility that 3 Atlas is made of materials and compounds that are unlike anything we've encountered before. Spectroscopic observations using the Very Large Telescope have revealed the presence of nickel vapor in the coma of 3 Atlas, which, on its own, there isn't necessarily strange. Nickel is commonly detected in comets. However, what's truly puzzling is that, unlike in most solar system comets, iron is conspicuously absent in the expected quantities. Normally, when nickel is detected in comets, iron is found in nearly equal proportions, as both elements tend to form together in the primordial materials that make up comets. 3 Atlas, however, is emitting nickel without any corresponding iron, suggesting that it formed under conditions far different from those in our solar system's nebula. Further analysis from the James Webb Space Telescope has uncovered another anomaly. The coma of 3 Atlas is overwhelmingly dominated by carbon dioxide, a composition never before seen in any known comet to this extent. The ratio of carbon dioxide to water is a staggering 7, low, which is one of the highest ever measured. Comets from our solar system typically show much more balanced ratios because they formed in regions where both water and carbon dioxide ices were stable. This carbon dioxide-heavy composition indicates that 3 Atlas likely formed far from its parent star, beyond what's known as the carbon dioxide frost line, a region so cold that carbon dioxide could condense into ice while water ice remained scarce. But there's even more to this mysterious object. Analysis of the cosmic ray exposure on 3 Atlas over its 7 billion year journey suggests that its outer layers have undergone profound transformation. The surface material has been significantly altered by radiation, breaking molecular bonds and forming new compounds. This has created a radiated crust that bears little resemblance to the pristine ices that would have originally formed this interstellar traveler. As 3 Atlas approached the Sun, the heating of this crust triggered chemical reactions that are vastly different from anything we've observed in comets that have spent their entire existence within the shelter of our solar system. This is the context we must consider when trying to understand the anti-tail. We are not simply looking at a typical comet with a rare viewing geometry. No, we are witnessing an object that has journeyed through interstellar space, formed in an alien environment, and accumulated damage over billions of years that we can't fully comprehend. As it approaches the Sun, 3 Atlas is responding in ways that our current models were never designed to predict. The anti-tail is not just strange, it is an unprecedented phenomenon that may require a rethinking of what we know about interstellar objects. Every part of 3 Atlas seems to challenge our understanding. The real question is whether these strange behaviors can be explained by natural processes we have never encountered before, or if there is something else at play here. Avi Loeb, a prominent Harvard astrophysicist, has raised the possibility that the sunward structure could be the result of concentrated light, suggesting that 3 Atlas might be self-luminous in the sunward direction. This would perfectly explain the persistent and structured feature we observe. Loeb himself doesn't claim that this is the most likely explanation. He has stressed that natural origins should still be considered the default hypothesis. However, he has also been vocal in asserting that the scientific community should remain open to alternative possibilities, especially when dealing with phenomena as peculiar as this one. Meanwhile, the mainstream scientific community has reacted with a more measured skepticism. David Jewitt, a UCLA astronomy professor who has spent years studying comets, suggests that the periodicity observed in the anti-tail could simply be the result of large dust particles ejected from the sun-facing side of 3 Atlas. These particles would naturally remain in the sunward direction, as they are less affected by solar radiation pressure than smaller particles. This is standard comet physics, and such occurrences have been observed in solar system comets, albeit less dramatically and persistently than in 3 Atlas. As the debate continues, what we know for sure is that 3 Atlas is displaying a feature that defies easy explanation. This antitail has existed for months, survived perihelion, and grown to a size larger than the distance from the Earth to the Moon. Multiple hypotheses have been suggested, but none have fully explained the phenomenon. In just 48 hours, 3 Atlas will reach its closest approach to Earth, providing one last opportunity to gather critical data that may resolve the mystery behind its strange behavior. But the antitail is not the only anomaly researchers have detected. There is also a rhythmic signal emanating from 3 Atlas, a periodic pulse that repeats with clockwork precision every 16 hours. This signal has been described by one researcher as a heartbeat echoing across the vast expanse of space. The brightness of 3 Atlas is not constant, but fluctuates in a regular rhythm, increasing by 20–40% every 16 hours before fading back down and starting the cycle again. The signal has been consistent since July, when systematic observations of 3 Atlas began. It continued through September as the comet approached the Sun, persisted through October when it reached perihelion at 246 Nula 8H, and continues into December as the comet races toward its closest approach to Earth. This 16-hour cycle was documented in a paper published in the journal Astronomy and Astrophysics, which details observations from research teams across Europe and Africa. The research team carefully measured the variations in brightness, accounting for changes in distance, viewing angle, and solar illumination. After making these corrections, they found a clear and unmistakable pattern. 3 Atlas is pulsing like a cosmic lighthouse, its periodic brightness variations creating a precise and predictable rhythm. The most straightforward explanation for this pulsing is rotation. If 3 Atlas has an elongated shape, its brightness would naturally vary as different parts of the object rotate into and out of view. This kind of behavior is common for asteroids and has also been observed in other comets. While a 16-hour rotation period is unusual, it is not unheard of. However, the degree of brightness variation up to 40% is harder to explain. For such a large variation, the shape of the object would need to be extremely elongated or flattened. Early analyses suggested that the object had an axis ratio of about 0 bar, but this was based on the assumption that the brightness variation was mainly due to the nucleus. Here's where things get really strange. The Hubble Space Telescope images show that most of the light we see from 3 Atlas does not come from the nucleus itself. Instead, it's coming from the coma, the massive cloud of gas and dust surrounding the nucleus. If the brightness changes were purely due to the rotation of the nucleus, the variation should be dampened by the steady glow of the coma. Yet the variation remains strong, which suggests that something else is at play. Avi Lowe has proposed an alternative explanation. He believes that the periodic brightening could be the result of discrete jets of outgassing from 3 Atlas, rather than the rotation of the nucleus. In this scenario, the jets erupt from specific areas on the surface of 3 Atlas. As the nucleus rotates, these active regions come into and out of sunlight, effectively switching on and off like geysers. When a volatile, rich region faces the sun, it heats up and erupts, flooding the coma with fresh material, which then scatters sunlight and increases the brightness. As the object rotates again, the eruption subsides, and the cycle repeats. If this explanation is correct, it would mean that the jets are not random. They are structured and synchronized to the rotation of the nucleus, potentially influenced by the object's internal geology and composition. This interpretation implies that the outgassing is not driven merely by solar heating, but by something more complex, perhaps the unique internal processes of an object that formed in a distant star system with conditions unlike anything in our solar system. The implications of this are profound. It suggests that 3 Atlas is not a passive comet, but an actively dynamic object, continually reshaping the structure of its coma through periodic pulses of outgassing. The material from these jets travels a significant distance, up to 25 kilometers before the next pulse occurs. This is far from the typical behavior of comets we observe in our own solar system. When you consider this against the backdrop of our previous experiences with comets, objects that are usually messy, unpredictable, and chaotic, 3 Atlas stands out as a highly structured and precise object. Its steady rhythm, like the pulse of a cosmic heart, raises a whole new set of questions about the nature of this interstellar visitor. There are natural explanations for the heartbeat. Of course, the pulsations could simply reflect the rotation of the nucleus or the distribution of volatile materials. Perhaps the rotation axis is stable, or the distribution of the material is unusually uniform, creating this precise, regular signal. But given how little we know about interstellar objects, we cannot discount the possibility that the explanation may be even more extraordinary. R.V. Lowe has even suggested the possibility that the periodic pulses could be the result of artificial propulsion, a subtle mechanism that could control the orientation or trajectory of 3 Atlas in ways we have yet to detect. Although this idea is highly speculative and lacks direct evidence, Lowe argues that the scientific community must remain open to alternative possibilities, especially when confronted with an object that behaves in ways we can't yet explain. While the scientific community remains cautiously skeptical of such claims, the regularity of the heartbeat provides a unique opportunity to study the internal structure of 3 Atlas. Each cycle of brightness variation offers new insights into how the nucleus is organized, how the volatile materials are distributed, and how they react to solar heating. These observations allow us to gather data on an object that formed 7 billion years ago, in a planetary system far beyond our reach, and that is now revealing its secrets piece by piece. As 3 Atlas reaches its closest approach to Earth, this rare opportunity will provide some of the most detailed and high-resolution images we've ever captured of such an object. The data collected during this critical time will likely answer many of the lingering questions surrounding its behavior, and may even help us understand how objects like this one interstellar visitors may shape the future of planetary defense. For a brief yet invaluable period, we are presented with our best opportunity to decode the peculiar heartbeat of 3 Atlas. But as time moves on, this chance will fade. The signal, which has resonated through the vast expanse of space, will gradually become harder to detect as 3 Atlas accelerates outward, back toward the interstellar void from where it originated. While the 16-hour rhythm will continue in its cosmic dance, our ability to observe it will slowly diminish. By the time spring arrives, the object will become too faint for most of the ground-based telescopes to capture. As the months pass, even the mighty Hubble Space Telescope will struggle to pick up the pulse, and eventually, the heartbeat of 3 Atlas will sink into the background noise of every instrument at our disposal, continuing on in the silent emptiness of space, unheard and unnoticed. There's a strange sense of poignancy in that. For an unimaginable 7 billion years, 3 Atlas has journeyed in silence through the vast expanse of the cosmos, emitting nothing, receiving nothing, and remaining unknown to any intelligence that may exist. Yet, for a fleeting moment in late 2025, it ventured close enough to a star to briefly stir from its slumber. As it passed through the warmth of the sun, its icy exterior began to sublimate, releasing jets of gas and dust. Its cosmic heartbeat, once undetectable, became a beacon of curiosity across the gulf of space. And for this brief window of time, a species on a small planet, orbiting a modest star, had the rare privilege to listen, to measure, to wonder. That window is nearly closed now. In billions of years, 3 Atlas may again pass near another star, perhaps awakening once more. Maybe by then, there will be someone there to hear it, someone who will detect the same rhythm we've heard and ask the same questions we're asking now. Or perhaps, after this journey, 3 Atlas will drift eternally, without another encounter, its heartbeat fading into the vastness of the universe, pulsing for no one. But for now, we are here, and we are listening. The heartbeat continues, marking a fleeting chapter in the story of our cosmos. However, as we dive deeper into the mysteries of this interstellar visitor, we uncover even more enigmas. Because 3 Atlas is not just pulsing, it is erupting. In recent observations from the past 2 weeks, something remarkable has been detected. 3 Atlas is covered in ice volcanoes, an extraordinary phenomenon we've rarely seen elsewhere in the solar system. These ice volcanoes are more active than anyone could have predicted. Images received in late November from the Joan Oro telescope in Spain revealed spiral jets of gas and dust shooting outward from the surface of 3 Atlas, curving as the object rotates beneath them. These patterns looked less like typical cometary outgassing and more akin to eruptions seen on icy moons in the outer reaches of our solar system. The researchers who studied these images came to a striking conclusion. 3 Atlas appears to be covered in cryovolcanoes, ice volcanoes actively erupting as the object passes close to the Sun. This behavior mirrors that of moons like Enceladus, a small satellite of Saturn, which erupts geysers of water ice hundreds of kilometers into space, or Triton, Neptune's moon, where nitrogen ice shoots out in dramatic plumes. Even Pluto, along with other trans-Neptunian objects, is suspected of harboring cryovolcanic activity due to their extremely cold conditions. Cryovolcanism involves the eruption of volatile ices instead of molten rock, driven by internal heat from sources like radioactive decay, tidal forces, or other forms of energy. This heat melts frozen volatiles beneath the surface, forcing them upward through cracks and vents, where they explode outward with incredible force. For 3 Atlas, the trigger is sunlight. As the object approached perihelion, the sun's heat began to penetrate deeper into its ancient, frozen surface. When the temperature reached the sublimation point for solid carbon dioxide, around -78 degrees Celsius, something dramatic happened. Rather than simply evaporating, the carbon dioxide ice destabilized, triggering a cascade of reactions that released far more energy than could be explained by passive solar heating alone. The research team studying these eruptions has proposed a fascinating mechanism. 3 Atlas, they argue, has a composition similar to a rare type of meteorite called carbonaceous chondrites. These meteorites are some of the most primitive objects in our solar system, containing abundant carbon compounds and crucial metals like iron and nickel. When the surface ice of 3 Atlas began to melt, the resulting liquid water didn't simply evaporate. Instead, it began to corrode the metal grains embedded within the cometary material, releasing energy and gases like carbon dioxide and hydrogen, which created a feedback loop, amplifying the initial solar heating into something far more explosive. This process may explain one of the most puzzling aspects of 3 Atlas, its sustained and global activity. Most comets, over time, develop a protective layer, an insulating crust of dust, and processed material that slows down outgassing. This is why older comets tend to be less active than newer ones. Yet 3 Atlas shows no evidence of such a protective crust. Its entire surface seems to remain active, venting material from multiple locations simultaneously, as if the protective layer never formed. The carbonaceous chondrite model provides a potential explanation if the composition of 3 Atlas promotes chemical reactions between water and metal. These reactions would continuously disrupt any crust that tried to form, keeping the surface exposed and vulnerable to solar heating in ways that typical comets are not. This continuous activity would explain why 3 Atlas shines so brightly as it approaches the Sun, maintaining a level of activity far longer than expected. The preprint paper outlining these findings was published on November 24th, and the scientific community is still grappling with the implications. If this hypothesis holds true, it would mean that 3 Atlas represents something fundamentally different from the comets we are familiar with in our solar system, an object whose internal chemistry drives its behavior in ways we've never seen before. There's also the possibility that 3 Atlas might not be as unusual as it seems. Perhaps most interstellar comets behave in similar ways, and we simply haven't had the chance to observe them closely enough. Our current sample consists of just 2 interstellar comets, Borisov and 3 Atlas. While Borisov behaved more like a typical solar system comet, it was smaller, fainter, and studied with far less intensity. 3 Atlas, by contrast, is brighter, closer, and being scrutinized by nearly every major telescope on Earth. Perhaps we are simply seeing details in 3 Atlas that were always present in interstellar comets, but went unnoticed in our previous, more limited observations. This highlights the challenge of working with such a small sample size. Every data point is crucial, and every anomaly carries enormous weight. It could be that 3 Atlas is typical of its kind, or it might be a freak of nature. We cannot know for sure without studying more interstellar visitors. Regardless of whether 3 Atlas is typical or unique, its cryovolcanic activity has implications for how we interpret other observations. The eruptions from its surface are not uniform. They emerge from specific locations with distinct orientations at particular times during its rotation cycle. This creates the complex, asymmetric structure in the coma that we observe. It also influences the periodic brightness variations we discussed earlier and may even contribute to the mysterious anti-tail, as material preferentially vents from the sun-facing hemisphere before being swept back by radiation pressure. Understanding where and when these eruptions occur is crucial to modeling the overall behavior of 3 Atlas. Each new observation brings us closer to unraveling the mysteries of this interstellar object. As we continue to piece together the puzzle of its origins, composition, and behavior, the spiral patterns observed in the images from the Spanish telescope reveal that the jets on 3 Atlas are not random or fleeting. Instead, these jets appear to be persistent, originating from specific surface locations that remain active as the comet's nucleus rotates. However, the intensity of these jets varies dramatically depending on the angle of solar illumination. When a vent rotates into direct sunlight, it erupts with violent force, expelling gas and dust into space. When it rotates into shadow, the eruption subsides but doesn't stop completely, suggesting that the heat stored in the comet's subsurface continues to drive outgassing even without direct solar illumination. This phenomenon is unlike what we observe on icy moons like Enceladus, where tidal heating provides a continuous energy source, independent of the sun's influence. For 3 Atlas, its cryovolcanism is entirely driven by solar energy. It is a passive response to external heating, rather than the internal processes we see on moons like Enceladus. However, the chemical reaction proposed by the carbonaceous chondrite model introduces a second energy source. As solar radiation interacts with the comet's surface, it generates additional heat through metal corrosion. This hybrid mechanism, solar energy combined with chemical reactions, could explain why 3 Atlas is exhibiting such intense activity, much more than what scientists initially anticipated. This insight has broader implications. If many interstellar comets share a composition rich in metals and possess chemically active interiors, then their behavior near stars would differ fundamentally from comets in our solar system. These interstellar visitors would likely light up more quickly, remain active for longer periods, and display dramatic eruptions, similar to what we're witnessing with 3 Atlas. Future surveys, such as the Vera Rubin Observatory, which will discover many more interstellar objects, could test this hypothesis. By comparing the chemical compositions of incoming interstellar visitors to their activity levels, scientists may be able to confirm whether this behavior is a common trait of interstellar comets. There's also a more speculative angle to consider. If the cryovolcanism on 3 Atlas involves liquid water even temporarily, even in small pockets beneath its surface, then this interstellar visitor may be carrying one of the essential ingredients for life as it journeys through the galaxy. The panspermia hypothesis, which suggests that life or its precursors could spread between star systems via objects like comets, has always been considered speculative but not impossible. If 3 Atlas contains liquid water, even briefly, it would be exactly the kind of vehicle that panspermia requires, one capable of carrying life or organic molecules across vast distances of space. In fact, NASA's ALMA observations have already detected hydrogen cyanide and methanol in the coma of 3 Atlas, both of which are considered important precursor molecules for the origin of life. The presence of these molecules, combined with evidence of internal chemical activity, paints an intriguing picture. This ancient interstellar visitor is not just a frozen relic of the past. It is chemically active, reacting and transforming as it passes through our solar system, just as life's building blocks are supposed to do. Let's be clear, though detecting life precursors is not the same as detecting life itself. Chemical activity, while interesting, is vastly different from biological activity. The presence of water, carbon compounds, and metals doesn't mean 3 Atlas is inhabited or ever was. However, it does suggest that the basic chemistry of life, as we understand it, can exist in objects that have drifted through interstellar space for billions of years, without the protection of a star system. It's an extraordinary idea the building blocks for life may be out there, drifting between the stars, ready to seed new worlds whenever an object like 3 Atlas passes through a planetary system. 3 Atlas will not impact Earth. It will not deliver its potential cargo of life-building materials to our planet. But someday, objects like it will. They always have. The early Earth was bombarded by comets carrying water and organic molecules, materials that may have contributed to the origin of life here. 3 Atlas reminds us that this process is not unique to our solar system. It is galactic in scope. The chemistry that sustains life flows between the stars, carried by ancient messengers like 3 Atlas, and we are only now beginning to understand their significance. The ice volcanoes continue to erupt. The jets continue to spiral outward, and 3 Atlas continues on its path toward its closest approach to Earth in just 2 days. But this journey began long before our solar system even existed. To understand where 3 Atlas came from, we must travel back in time 7 billion years to a galaxy that looked very different from the one we know today. 7 billion years of cosmic radiation before Earth existed, before the sun ignited, and before the cloud of gas and dust that would eventually form our solar system began to collapse. 3 Atlas was already ancient by the time our solar system was born. Best estimates suggest it formed in a planetary system that lived, evolved, and perhaps died, while the matter that would become Earth was still scattered across an uncharted region of the galaxy. 7 billion years ago, the universe was still in its infancy. The Milky Way was younger and more chaotic, still in the midst of merging with smaller galaxies, and still forming stars at a far higher rate than it does today. The chemical composition of the galaxy was different then. There were fewer heavy elements, like iron and oxygen, which form the basis for rocky planets and life as we know it. Stars formed during that time contained fewer metals and other key ingredients needed for the building blocks of life. This matters because 3 Atlas carries with it the signature of that ancient era. Its composition, the unusually high ratio of carbon dioxide to water, the presence of nickel without iron, and the extreme radiation exposure of its surface are all clues to the conditions in which it formed. When we study 3 Atlas, we are not just studying a comet, we are looking through a window into the early galaxy, into a time and place that no longer exists anywhere in the universe. A study published in late October analyzed James Webb's observations of 3 Atlas and concluded something remarkable. The object's extreme carbon dioxide enrichment could be explained by billions of years of exposure to galactic cosmic rays. Galactic cosmic rays, unlike the gentle solar radiation that warms planets, are the most energetic particles in the universe. Protons and heavier nuclei, accelerated to nearly the speed of light by supernova explosions and neutron star collisions, penetrate deep into unshielded material, ionizing atoms and breaking molecular bonds. For 7 billion years, 3 Atlas has been bombarded by these high-energy particles, which have fundamentally altered its surface chemistry. In contrast, comets in our solar system, which typically spend their time protected in the Oort cloud, are not exposed to such intense radiation. Interstellar comets like 3 Atlas, however, pass through the galactic disk exposed to the full intensity of cosmic rays. Over time, the damage accumulates, changing the chemical makeup of the comet. The cosmic radiation has created a thick, radiated crust on 3 Atlas, perhaps several meters deep, in which the original icy materials have been transformed into something entirely different. As the object approached the sun, this radiation-processed crust began to sublimate, releasing volatile compounds that had been locked away for billions of years. These chemical reactions are not just about ice sublimation, they are about the release of new, transformed materials that no comet in our solar system has ever experienced. This is why 3 Atlas behaves so differently from solar system comets like Borisov. It is not just from another place in space. It is from a different time and a different galactic environment, carrying within it the accumulated damage of cosmic rays that have bombarded it for billions of years. The antitail, the unusual composition, the extreme carbon dioxide ratios, and the cryovolcanic activity, these are all products of 7 billion years of cosmic radiation exposure. There's something almost philosophical about this. 3 Atlas has been irradiated by the death of countless stars. Every supernova, every stellar explosion, contributed to the cosmic ray flux that shaped this object. This radiation, this energy, all washed over 3 Atlas as it drifted through the galaxy. In a very real sense, this object carries within it the combined influence of generations of stars that no longer exist. The galaxy 3 Atlas traveled through wasn't always a hospitable place. There were periods of intense star formation when cosmic radiation was far more intense than today. Times when supernova rates peaked, and the radiation flux was overwhelming. There were likely close encounters with other stars, gravitational forces that altered its trajectory, leaving no visible trace. The surface of 3 Atlas bears the scars of all of these events. Scientists have traced 3 Atlas's path backward through time, identifying stars it may have passed near in the last 10 million years. They found 25 candidates, stars that came within about 1 parsec of its trajectory. But a span of 10 million years is nothing compared to 7 billion. Most of 3 Atlas's journey remains unknown, a dark and mysterious stretch of time when anything could have happened. And here is where speculation becomes irresistible. If 3 Atlas formed in a planetary system 7 billion years ago, what was that system like? Did it have planets? Could life have developed there? And if it did, could traces of that life still be hidden within the icy layers of 3 Atlas, protected from cosmic rays by its surface ice? The answer is likely no. The radiation would have destroyed any complex organic structures long ago. But that does not stop the imagination from wondering. 3 Atlas is a messenger from a distant time and place, a remnant of a system that no longer exists. The parent star that warmed it is likely gone, having collapsed into a white dwarf or exploded in a supernova. Whatever planets once orbited that star are lost to time. 3 Atlas, however, remains. It is the only surviving witness to a story we will never fully know. The data we gather from this fleeting passage represents our only chance to interrogate that ancient witness. Every spectrum, every measurement, every observation of its jets and coma structure helps reveal the history of its formation, its journey, and the cosmic environment it has traveled through for 7 billion years. The James Webb Space Telescope will observe 3 Atlas again this month, providing some of the most valuable data of the entire campaign. These observations will help refine our understanding of this remarkable object, its activity, and the forces that shaped it. As it moves away from the Sun, the observational challenges of solar glare will diminish, allowing for clearer views of its unique features. And as the months pass, Hubble and ground-based telescopes will continue monitoring it. Eventually, 3 Atlas will fade from our view. But the data we collect now will allow researchers to piece together a portrait of an object that has traveled farther and for longer than any comet we have ever studied. But there's one more piece of data worth noting. In late November and early December, 2 X-ray telescopes turned their instruments toward 3 Atlas, capturing something never seen before, the first X-ray images of an interstellar comet. What they found adds yet another layer to the mystery, offering more evidence that this object is unlike anything we've observed in our solar system. There is one more remarkable observation that demands our attention. During late November and early December, 2 X-ray telescopes turned their instruments toward 3 Atlas and captured something entirely unprecedented, the first X-ray images of an interstellar comet. The discovery added yet another layer to the growing mystery surrounding this celestial wanderer. It provided an important piece of data that doesn't align with conventional expectations, encouraging astronomers to think deeper and reevaluate their assumptions about interstellar objects. The X-ray glow detected on December 3rd, Liangtianling Arshawu, significantly altered our understanding. The European Space Agency's XMM Newton spacecraft focused its sensitive cameras on a specific patch of sky in the constellation Leo and held its gaze for an entire 20 hours. The target was, of course, 3 Atlas. Using the European Photon Imaging Camera, the most sensitive X-ray detector in the telescope's array, researchers obtained the first X-ray image ever captured of an interstellar comet. This image immediately raised questions that scientists are still grappling with. The X-ray image revealed 3 Atlas as a bright red glow against the dark blue expanse of empty space. The red indicates low-energy X-rays, photons with wavelengths much shorter than visible light, far more energetic than the radiation our eyes can detect. What's astonishing is that these X-rays should not even exist, at least not in the way they are being observed. Comets are cold, inert objects, lacking the nuclear reactions or extreme temperatures necessary to produce high-energy radiation. And yet, there it was a distinct X-ray signature emanating from this interstellar visitor as it sped through our solar system. The key to this phenomenon lies not in the comet itself, but in the surrounding environment. As 3 Atlas travels through the inner solar system, it sheds vast quantities of gases such as water vapor, carbon dioxide, and carbon monoxide, all of which sublimate from its frozen surface. These gases stream outward, forming a coma that envelops the nucleus of the comet. At the same time, the solar wind, a constant stream of charged particles emanating from the sun at incredibly high speeds, slams into this expanding gas cloud. This collision between the solar wind and the coma gas triggers an extraordinary process. The solar wind ions capture electrons from the cometary gas, a process known as charge exchange. This interaction leaves the solar wind particles in an excited state, and as they return to their ground state, they release energy in the form of X-rays. This means that the entire coma becomes a diffuse X-ray source, glowing in wavelengths far beyond our ability to see, but perfectly detectable by specialized instruments like XMM Newton. While this process of X-ray emission has been observed before in solar system comets, 3 Atlas is the first interstellar comet to be detected in this way. This historic observation opens up unique avenues for understanding the comet's composition insights that other wavelengths of light simply cannot provide. X-ray emission is especially sensitive to certain elements, like hydrogen and nitrogen, which produce distinct X-ray signatures when involved in charge exchange. These elements are notoriously difficult to detect using optical or infrared telescopes, but they light up vividly in X-ray observations. This is significant because one of the mysteries surrounding the first interstellar object, Oumuamua, was whether it contained exotic ices such as frozen nitrogen or hydrogen. Some researchers speculated that Oumuamua might have been a fragment of a nitrogen ice glacier from a Pluto-like world in another solar system. The unusual acceleration observed in Oumuamua was thought to be caused by nitrogen sublimation, not by the typical outgassing of water or carbon dioxide, but this hypothesis was never testable. Oumuamua was already beyond reach before anyone could observe it in X-rays. But now, 3 Atlas provides the opportunity that Oumuamua denied us. The X-ray observations could reveal whether hydrogen or nitrogen are present in significant quantities, providing direct evidence of the composition of this interstellar object information that would otherwise remain hidden. If 3 Atlas displays the same chemical signatures seen in solar system comets, it suggests that interstellar visitors are not fundamentally different from our own solar system's comets. But if it shows anomalies, particularly an excess of hydrogen or nitrogen, it could validate the exotic ice hypotheses once proposed for Oumuamua. The XMM Newton data is still being thoroughly analyzed, and full results have yet to be released. However, preliminary findings indicate that 3 Atlas is indeed emitting X-rays in exactly the manner predicted for a comet interacting with the solar wind. The detection itself is a historic milestone. This is the first time we've captured an interstellar object in this particular wavelength. Just a few days before the XMM Newton observation, another X-ray telescope, XRISM, a Japanese X-ray astronomy satellite, also captured a historic image of 3 Atlas. XRISM's soft X-ray telescope, known as X10, independently observed the object, confirming the detection and providing additional data points for calibration and analysis. The importance of these X-ray observations is amplified by their complementarity with other wavelengths. The James Webb Space Telescope has already provided infrared spectra, revealing the presence of carbon dioxide, water, and carbon monoxide in the coma. Optical telescopes have captured stunning images of the coma structure and jets, while ultraviolet observations have detected the breakdown products of water. Now, with the addition of the X-ray data, we can complete the picture. This multi-wavelength approach allows us to study 3 Atlas from a variety of angles, each offering a unique perspective on the object. Each wavelength sees something different, providing invaluable insights that couldn't be obtained from any single source alone. The collaboration between multiple space agencies and observatories from around the world has been essential in this effort. The scientific research on 3 Atlas requires both breadth and depth, combining data from different instruments and perspectives to create a comprehensive understanding of this interstellar visitor. These combined efforts are why 23 nations have contributed observations, all working together to unlock the secrets of this ancient object. The X-ray observations also give us valuable information about the structure of the coma. Since X-rays are produced by the interaction between the solar wind and the cometary gas, the brightness distribution in an X-ray image traces the density of that gas at different distances from the nucleus. The XMM Newton image reveals that 3 Atlas has a substantial and extended coma, a finding that supports what optical observations had suggested, but provides independent verification through an entirely different physical process. The X-ray data reveals subtleties that researchers are still working to understand. For example, the energy spectrum of the X-rays holds clues about which elements are responsible for the emission. The spatial distribution of brightness in the coma could point to asymmetries, potentially correlating with the jets and the antitail observed at other wavelengths. Additionally, the time variability of the X-ray flux may correlate with the 16-hour brightness pulsation observed in optical data. Analyzing this X-ray data will take time, as it's notoriously difficult to work with. Careful calibration and background subtraction are required to extract meaningful signals. The 20-hour integration time used by XMM Newton was essential because 3 Atlas is faint in X-rays, much fainter than the bright sources these telescopes typically observe. Extracting a signal from the noise is a painstaking process, and the full scientific results may not emerge for several months. But the image itself, the red glow of 3 Atlas against the dark blue void, carries meaning far beyond the numbers it encodes. This image marks the beginning of a new chapter in our understanding of interstellar objects. It proves that we can study these visitors in wavelengths that unveil their deepest secrets. It validates the multi-wavelength approach to planetary science, reminding us that every tool we create, every instrument we launch, and every new way of observing the universe holds the potential to reveal phenomena we could never have discovered otherwise. The timing of the X-ray observations was not a coincidence. On December Dryad, 3 Atlas was 282 million kilometers from Earth, close enough for detection, but far enough from the Sun to minimize interference from solar X-ray emission. By mid-December, the object had moved even closer, but it had also passed its perihelion, meaning its outgassing was likely beginning to decrease. The X-ray window for observing 3 Atlas was narrow, and conditions had to be perfect for the telescopes to collect high-quality data. As 3 Atlas reaches its closest approach to Earth in just 2 days, the X-ray telescopes will no longer be observing it. Their science was completed earlier, when the geometry was optimal for detection. However, other instruments will continue monitoring the object. Ground telescopes across the globe will track it as it moves through the dark skies of the new moon. And space-based observatories will capture additional data that will take months to analyze. Somewhere within the vast amount of data collected, there may be answers to the questions we've been asking since July. But the questions surrounding 3 Atlas have not only been raised by space agencies and professional astronomers, they have been amplified, distorted, and in some cases complicated by one particular voice, the renowned Harvard astrophysicist, Avi Loeb. His name, Avi Loeb, has surfaced in nearly every conversation surrounding this interstellar traveler, and his interpretations have profoundly shaped public perceptions in ways the scientific community struggles to counteract. Loeb, a prominent Harvard astrophysicist, is not one to stay quiet about his views. Although he prefers the nickname Avi, he holds one of the most esteemed positions in American astronomy, leading the Galileo Project, founding the Black Hole Initiative at Harvard University, and serving as the director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. His resume is beyond reproach, with hundreds of peer-reviewed papers to his name. showcasing his esteemed reputation. His credentials are rock solid, but within the astronomical community, he has become a deeply polarizing figure. Some of his colleagues respect his intellect, but there is a palpable frustration with his persistent promotion of ideas that many feel the evidence does not support. Loeb, however, firmly believes that we should take the possibility seriously that 3 Atlas is not just a comet, but something far more enigmatic and potentially artificial in nature. Let me clarify what this means and what it does not. Loeb has never claimed that 3 Atlas is definitively an alien spacecraft. On the contrary, he has repeatedly stated that natural explanations remain overwhelmingly more likely. He has acknowledged that 3 Atlas behaves like a typical comet in many ways, such as having a coma and outgassing, and following a trajectory consistent with gravitational dynamics. Yet, Loeb has argued that the scientific community has been far too eager to dismiss alternative hypotheses, too quick to conclude that 3 Atlas is just another ordinary comet before the data is fully explored. He believes there is an undue influence from what he refers to as sociological pressures, urging scientists to conform to widely accepted narratives. This is the same argument he made in 2017 regarding Oumuamua, and it sparked massive controversy within the scientific community. Oumuamua displayed several unusual characteristics: an extreme, elongated shape, an unexplained acceleration away from the sun, and a complete lack of visible outgassing. Loeb co-authored a paper proposing that these features were consistent with a light sail, an artificial structure designed to be propelled by radiation pressure, rather than a natural object. The paper, though technically rigorous, suggested that Oumuamua could be of technological origin. This conclusion ignited a fierce backlash that still lingers today. Critics argued that natural explanations could account for every anomaly that Oumuamua displayed. The elongated shape might have resulted from a collision or tidal disruption. The unexplained acceleration could have come from outgassing of volatile compounds like nitrogen or hydrogen substances our instruments are not yet equipped to detect. The lack of a visible coma could simply mean that Oumuamua had been depleted of the ices that typically produce cometary tails. None of these explanations required invoking aliens. Critics argued. They favored simpler, natural hypotheses, following the principle of Occam's razor, which suggests that the simplest explanation is usually the best. Loeb responded by challenging this use of Occam's razor, suggesting that it should not be employed to dismiss hypotheses before they are properly tested. He argued that the very act of dismissing the technological hypothesis was itself a form of bias, a sociological, not scientific, judgment. His argument is that, since we've never looked for such objects before, we have no basis for assuming that technological artifacts are rare in interstellar space. The absence of evidence, Loeb insists, is not evidence of absence. This philosophical stance has now been transferred to 3 Atlas. Loeb has catalogued what he terms the anomalies of the object features that do not fit neatly into conventional models. These anomalies include the anti-tail that points toward the sun, the extreme carbon dioxide ratio, the 16-hour periodic brightness pulsation, the non-gravitational acceleration, the unusual nickel-to-iron ratio, and the extreme irradiation signature. Each of these features, he argues, deserves serious investigation rather than being dismissed outright. Loeb has become a central figure in the public conversation about 3 Atlas, often publishing nearly daily updates on his widely followed blog. In his posts, he meticulously analyzes new images, proposes theoretical explanations, and sometimes speculates on what it would mean if these anomalies turned out to be artificial in nature. His blog posts have a massive audience, sparking heated discussions among both laypeople and scientists. A recent analysis by the University of Washington revealed that out of 700,000 posts on social media about 3 Atlas, approximately 40% mentioned aliens or extraterrestrial technology. Over 130,000 posts referenced Loeb by name, with 63% of those connecting him directly to the alien hypothesis. Loeb's visibility in the public discourse has made him a target for criticism from many in the scientific community, who argue that his speculations about alien involvement are irresponsible. One of Loeb's most vocal critics is Jason Wright, an astronomer at Penn State who himself works on technosignatures and the search for extraterrestrial intelligence. Wright has written detailed rebuttals to Loeb's claims about 3 Atlas, arguing that Loeb consistently overstates the anomalies, downplays natural explanations, and frames the debate in a way that unfairly suggests mainstream scientists are closed-minded instead of being appropriately skeptical. The specific criticisms are both technical and detailed. For example, when Loeb suggested that the lack of a traditional cometary tail might indicate that 3 Atlas wasn't outgassing as expected, Wright pointed to images that clearly showed comet-like structure. When Loeb proposed that the anti-tail might be a beam of self-generated light, other researchers noted that similar sunward enhancements have been observed in solar system comets and could be explained by the presence of large dust particles that resist radiation pressure. Regarding Loeb's emphasis on the unusual composition of 3 Atlas, planetary scientists remind us that we have only studied 3 interstellar objects, making it impossible to know what is typical for this type of comet. At a NASA press conference on November 19th, officials directly addressed the alien speculation. Associate Administrator Amit Chatria clearly stated that 3 Atlas is a comet, that it behaves like a comet, and that all available evidence points to it being a natural object, with no need to invoke extraordinary explanations. This was a deliberate choice of language, as NASA aimed to counter the growing narrative around 3 Atlas that had been amplified by Loeb. Even though he remained technically accurate in his individual claims, Loeb responded on his blog, expressing frustration with the press conference. He criticized NASA for not addressing the anomalies he had identified, specifically questioning why they had not mentioned the mystery of the anti-tail. Loeb suggested that the agency was prioritizing public relations over scientific transparency, a sentiment that only furthered the tension between his approach and the more cautious, institutional mindset of major space agencies. I want to be fair to both sides of this debate because both sides raise valid points. Loeb is right that anomalies deserve serious investigation, and he is correct that prior assumptions can bias scientific interpretation. He is also right to argue that we have almost no data on interstellar objects and should approach our conclusions with humility. The history of science is replete with examples where mainstream opinions were wrong, where anomalies dismissed as insignificant later proved to be revolutionary. However, critics are equally correct in their stance that extraordinary claims require extraordinary evidence. They are right that natural explanations should be thoroughly exhausted before jumping to artificial ones. They are also correct in asserting that amplifying the alien hypothesis, even with caveats, can contribute to misinformation and undermine public trust in scientific institutions. The social responsibility of scientists includes not just being technically accurate, but also being mindful of how their words will be interpreted and used by the public. The ongoing debate surrounding Loeb has become almost as interesting as the mystery of 3 Atlas itself. It raises critical questions about how science should communicate uncertainty, how much speculation is appropriate in public discourse, and who gets to define the boundaries of legitimate inquiry. Loeb sees himself as a champion of open-minded science, willing to entertain possibilities that other scientists find uncomfortable. His critics, however, view him as someone who has strayed from rigorous standards in pursuit of publicity and book sales. The truth likely lies somewhere in between. Loeb is not a charlatan. His scientific work is generally solid. His specific analyses of the anomalies in 3 Atlas are technically defensible, even if some of his interpretations are disputed. Yet, he has deliberately positioned himself as a provocateur, challenging consensus and courting controversy. This positioning has made him highly influential in the public discussion about interstellar objects, but it has also marginalized him in some parts of the professional community. What matters, for now, is not whether Loeb is right or wrong about 3 Atlas. What matters is that his questions have forced the scientific community to look more carefully at this interstellar visitor, to document anomalies that might have otherwise been dismissed, and to consider alternative hypotheses that might have otherwise been ignored. Even if 3 Atlas turns out to be a completely natural comet, the scrutiny it has received due to Loeb's advocacy will have ultimately resulted in better science, more thorough documentation, and a clearer understanding of what we do and do not know. In just about 36 hours, 3 Atlas will reach its closest point to Earth. The data collected during that critical window won't necessarily settle the debate surrounding its origins. In fact, it will likely raise new questions as quickly as it answers old ones. But it will add invaluable insight to the permanent record of what this ancient interstellar traveler has revealed during its brief passage through our solar neighborhood. And that record, more than any individual interpretation, is what will ultimately matter. The data collected during this critical window of observation will not settle the debate. In fact, it will likely raise as many new questions as it answers. Yet it will significantly contribute to the permanent record of what this extraordinary interstellar visitor has revealed during its brief passage through our cosmic neighborhood. This data will add value not just to our understanding of 3 Atlas, but also to the broader field of space exploration and interstellar objects. And in the end, this growing record, more than any singular interpretation or theory, will hold the key to our understanding of this mysterious object and its journey across the stars. The moment of closest approach is now just around the corner. December 19th, Wu, at precisely 6 minutes past midnight, Coordinated Universal Time, is the scheduled moment when 3 Atlas will reach its closest point to Earth. As we approach this moment, it's crucial to examine the circumstances surrounding it, especially the alignments and coincidences that have framed this entire event. December 19th at 06:02 UTC. 3 Atlas will be at the peak of its approach, and while orbital mechanics are unforgiving, their precision is unmatched in ensuring the trajectory of celestial objects. Orbital mechanics do not care about human schedules or convenience. They are based purely on mathematical predictions that describe the movement of objects in space. They calculate positions and trajectories with such accuracy that we can predict exactly where an object like 3 Atlas will be at any given moment, and how close it will come to Earth. According to these mathematical models, 3 Atlas will reach its closest approach to Earth at 06:02 UTC on Friday, December 19th, Wu, when it will be approximately 268.9 million kilometers away from our planet. While this distance is vast by human standards, it is relatively close when viewed from the perspective of interstellar space. It's about 8 times the distance between Earth and the Sun, far beyond the range of any spacecraft we currently possess, and too distant to be visible to the naked eye, even under ideal conditions. But in the context of the 7-billion-year journey this object has made across the vastness of space, this is nothing short of intimate. It's worth noting that the timing of 3 Atlas's closest approach carries additional significance, which has not gone unnoticed by astronomers and observers worldwide. December 19th coincides with a new moon phase, which means the sky will be exceptionally dark, providing perfect conditions for astronomical observation. As Avi Loeb pointed out in one of his insightful blog posts, nature is offering Earthlings a rare gift, optimal viewing conditions, precisely when they matter most for studying this cosmic visitor. 3 Atlas will be positioned in the constellation Leo, visible in the pre-dawn sky for observers in the northern hemisphere. Technically, anyone with a sufficiently powerful telescope will be able to observe it. Though visible might be too generous a term, at its current magnitude of around 11 or 12, the object is roughly 100 times fainter than the faintest stars visible to the naked eye. To spot it, you would need at least a 6-inch telescope, and even then, it would appear only as a faint, indistinct smudge. For amateur astronomers with more advanced setups, such as tracking mounts and sensitive cameras, 3 Atlas presents a more rewarding target. Through long exposures, the structure of the coma and spiraling jets can be captured, and perhaps even hints of the mysterious anti-tail that has perplexed scientists since the object was first discovered. Recent images from amateur astronomers have shown 3 Atlas taking on a distinct greenish hue, likely due to diatomic carbon being excited by solar radiation. This green glow is a recent development that has only emerged after perihelion, further confirming that 3 Atlas is evolving as it interacts with our solar environment. During this crucial observation window, professional observatories will remain vigilant. The Virtual Telescope project in Italy has already scheduled a free live stream for December 18th, starting at 11 p.m. Eastern Time, 4 a.m. GMT on December 19th. Viewers around the world will be able to witness the close approach of 3 Atlas in real time. Meanwhile, other observatories across multiple continents will continue to gather data, all feeding into the International Asteroid Warning Network's campaign, which has been tracking this object with unprecedented intensity. The James Webb Space Telescope, still in operation, is also expected to observe 3 Atlas again this month. Although the exact timing of these observations remains undisclosed, Hubble will continue its monitoring efforts, and ground-based spectroscopic facilities will work to detect changes in the chemical composition of the comet's outgassing as it moves further away from the Sun. Every major observatory that can access the object's trajectory will be involved in collecting data that will fuel scientific research for years to come. But there's more to December 19th than just this extraordinary celestial event. It falls right in the middle of the largest planetary defense exercise ever conducted, which began on November 27th and will continue through January 27th. The closest approach of 3 Atlas is not only an astronomical milestone, but also the centerpiece of a global effort to test and refine planetary defense protocols. Involving 23 nations, this exercise is coordinating observations, testing protocols, and evaluating the ability of various space agencies to track and characterize fast-moving objects from outside our solar system. The exercise has already delivered impressive results. For example, the European Space Agency reported that data from the ExoMars Trace Gas Orbiter, combined with ground-based data, improved predictions of 3 Atlas's trajectory by a factor of 10, an extraordinary leap in our tracking capabilities. The precision with which we now know where 3 Atlas has been, where it is going, and where it will be in the future would have been impossible even just a decade ago. The combination of spacecraft at different vantage points, ground telescopes across continents, and sophisticated orbital modeling has created a tracking infrastructure that represents the cutting edge of planetary defense. But the real question being posed by this exercise is not about 3 Atlas specifically, it's about the next object that might come our way. What if the next interstellar visitor does not give us 5 months of warning before its closest approach? How quickly can the global network detect a fast-moving target? How swiftly can preliminary observations be refined into accurate trajectories? How effectively can data flow between international agencies that do not always share information easily? And perhaps most critically, how well can public communication strategies be executed to prevent the spread of misinformation and manage the inevitable speculation that accompanies any unusual astronomical event? These are the questions that keep planetary defense officials awake at night. While 3 Atlas poses no threat to Earth, its velocity of 60 kilometers per second shows just how quickly things could change if an object like this were discovered on a collision course with our planet. In that case, the warning time could be measured in weeks, not months, making early detection, rapid characterization, and global coordination even more critical. The successful deflection of an asteroid demonstrated by the DART mission showed that we can indeed alter the trajectory of a hazardous object if we have enough time. But enough time only comes with early detection, precise characterization, and international collaboration. The ongoing 3 Atlas campaign is putting all of these capabilities to the test, and the results so far have been promising. The International Asteroid Warning Network has operated as planned, with over 80 observers contributing real-time data to a unified tracking effort. Coordination between agencies has been efficient, with ESA, NASA, JAXA, and others sharing information swiftly. However, the public communication challenge has proven to be more difficult. The surge of alien speculation online has overshadowed factual reporting in many places, complicating the task of managing public expectations. But this, too, is a learning experience. The next time an unusual object appears, space agencies will be better prepared to understand how narratives form and spread, and how to counteract misinformation before it takes hold. December 19th will be a final test of these systems before 3 Atlas begins to fade from view. The data gathered during closest approach will be some of the most valuable in the entire campaign. It will capture 3 Atlas at its brightest, closest, and most detailed, providing an unprecedented opportunity for researchers to observe and analyze this interstellar object in real time. Whatever anomalies remain unresolved, whatever questions persist, the observations from this critical window will offer the best chance to uncover answers. After that, however, it will be over, not abruptly, but gradually, as 3 Atlas continues its journey outward, moving away from the Sun and back toward the interstellar void from which it came. By March, it will pass within about 53 million kilometers of Jupiter, close enough for a brief gravitational interaction with the gas giant, but not enough to significantly alter its course. In the mid-2030 seconds, 3 Atlas will cross back into interstellar space, leaving our solar system behind forever. As it drifts away, its ice volcanoes will go dormant, its heartbeat will fade, and its coma will dissipate into the vast vacuum of space. Ultimately, only the cold, dark nucleus of this ancient traveler will remain, carrying the secrets of its 7-billion-year journey into the endless night. We will never see it again. No human being, no future civilization, no species that may arise on Earth or elsewhere in our solar system will ever have another opportunity to study this particular object. 3 Atlas came from a place we cannot identify, formed under conditions we can only imagine, and carries with it secrets we may never fully unravel. For a brief moment in time, 3 Atlas passed close enough for us to examine. That window is rapidly closing. But there's one final layer to this story, one last piece of meaning that ties everything together, something I've been building toward throughout this discussion. It concerns the timing, the coincidences, and the remarkable alignments that have framed this entire event from the moment 3 Atlas was first discovered. When you step back and look at the whole picture, when you consider everything happening simultaneously, the term coincidence begins to feel inadequate. Let me walk you through the timeline of the past 6 months, not to argue for any particular conclusion, but simply to show you the pattern that has unfolded. And you can decide for yourself what it means. You are welcome to draw your own conclusions from the sequence of events leading up to this moment. Let's examine the timeline that has unfolded over the last 6 months, not to advocate for any specific viewpoint, but simply to highlight the pattern that has emerged. On July 1st, downtilling Asteroid, the Atlas telescope in Chile first detects a faint object moving across the backdrop of stars. Within days, astronomers confirm its hyperbolic trajectory, confirming it as an object from interstellar space. This makes it only the 3rd such object ever confirmed. In August, the Hubble Space Telescope captures the first detailed images of this object. The images reveal a teardrop-shaped coma with an unusual extension toward the Sun, an anti-tail that defies conventional understanding. The James Webb Space Telescope follows up with infrared observations, showing extreme enrichment in carbon dioxide, unlike anything seen in solar system comets. In September, 3 Atlas approaches Mars, with the ESA's Mars Express and ExoMars orbiters capturing images from less than 30 million kilometers away. The composition of the object continues to puzzle researchers, with evidence of nickel without iron and compounds such as methanol and hydrogen cyanide, molecules that are key to the chemistry of life. In October, 3 Atlas reaches perihelion, racing around the Sun at nearly 250. Solar observatories track it through the glare. By the time it emerges on the other side, significant changes are evident. The coma is larger, the activity more intense, and the greenish glow from diatomic carbon has appeared. By November, NASA holds a press conference explicitly addressing the growing alien speculation surrounding 3 Atlas, confirming that the object is a comet. Nothing more. The very same week, the United Nations activates its largest planetary defense campaign to date, focusing on this interstellar object. 23 nations participate, and the European Space Agency secures a record budget, underscoring that planetary defense is no longer science fiction. Then, in December, X-ray telescopes capture the first-ever X-ray images of an interstellar comet. Amateur astronomers document the anti-tail extending an astonishing 500,000 kilometers. The heartbeat pulsation continues its regular 16-hour rhythm, while cryovolcanic eruptions persist. On December 19th, 3 Atlas will reach its closest approach to Earth, passing within 269 million kilometers during a new moon phase, offering optimal conditions for observation, perfect timing for those who have been closely following its passage. Now, consider the series of coincidences that have shaped this entire event. The third interstellar object ever discovered arrives just as humanity has developed the technological capability to study it in unprecedented detail. It approaches Earth at a time when every major space telescope is fully operational, and it reaches closest approach during a new moon phase that eliminates observational interference from the lunar glare. Furthermore, its passage triggers the largest planetary defense exercise in history, stress testing systems that would be required in the event of a future threat. This exercise spans from late November through late January, perfectly bracketing 3 Atlas's closest approach, as if the timeline had been deliberately aligned. I'm not suggesting that this was planned, nor am I implying that 3 Atlas is anything other than what NASA states a natural comet from another star system. The coincidences I've outlined are just that, coincidences. They can be explained by probability, by the fact that we observe what we are capable of observing, by selection effects that make certain events more likely to come to our attention. But there's something remarkably perfect about the alignment of all these factors. An object older than our solar system, having traveled for 7 billion years through the galaxy, arrives at this precise moment in human history. We happen to be at the right technological level to observe it, to study it, and to learn from it. We have instruments in space, at Mars, and even en route to Jupiter, all able to contribute observations. We also have global coordination mechanisms in place to share data across national boundaries. Everything seems to line up, and perhaps this is simply what the universe does. Maybe interstellar objects pass through our solar system regularly, tens of thousands of them at any given moment, according to statistical models, but we never noticed them before because we didn't have the tools to detect them. Maybe 3 Atlas is not special at all, just the first member of a vast population of interstellar visitors that we are finally able to perceive. In 10 years, once the Vera Rubin Observatory begins its search, we might look back at our current fascination and think, of course, interstellar visitors exist. They pass through our solar system regularly, but for now, in December 2025, 3 Atlas feels special. It feels like a message. Even if we can't decipher the language, it feels like an invitation, even though we may not know where we're being invited to. It brings with it the chemistry we recognize: carbon, water, and the building blocks of life. Its behavior is unlike anything we've fully explained. Yet it arrives at a time when we are prepared to notice, just as we are beginning to grasp what it is revealing. I don't know exactly what to make of that, and I'm not sure anyone does. What I do know is that the next 48 hours will be crucial. The data collected during closest approach will be analyzed for months, perhaps even years. Researchers will publish papers that address the anti-tail, the heartbeat, the cryovolcanism, and the composition. Some mysteries will be solved, while others will deepen. And eventually, when 3 Atlas has faded beyond our ability to observe it, we will be left with whatever conclusions we've managed to draw. These conclusions will shape how we think about the universe, our place within it, and the objects that drift through space, carrying histories we can barely comprehend. 3 Atlas is a messenger. We may never fully understand its message, but the effort to decode it has already changed us. As I record these words, 3 Atlas is closer to Earth than it has ever been before, and it will never be this close again. Telescopes across the globe are focused on the same patch of sky. Space agencies across 6 continents are coordinating observations, tracking an ancient object from another star, another time, and another place. This interstellar traveler is passing through our cosmic neighborhood, offering us one final, fleeting glimpse before it disappears forever into the darkness between worlds. Take a moment to think about that. Let it sink in. And if you've stayed with me through this entire journey, through the science, the speculation, the anomalies, and the explanations, the coincidences, and the questions they raise, I want to thank you. This is why I make these videos. This is why I dedicate hours to researching, writing, and trying to capture something true about the universe we inhabit. Because moments like this matter. They connect us to something larger than our daily concerns, something older than our species, something more vast than any single mind can fully comprehend. 3 Atlas has been traveling through space for 7 billion years. It paused in our solar system for a few brief months. And now, it continues its journey toward an unknown destination beyond the reach of any telescope we will ever build. We were lucky to see it. We were lucky to be here at this moment, equipped with the right tools and the capacity to wonder. If this content has meant something to you, please consider sharing it with someone who might also appreciate it. Subscribe if you haven't already, and leave a comment sharing your thoughts on whether the coincidences we've discussed feel meaningful or simply random. I read every response, and your engagement shapes what I create next. Thank you for watching. Thank you for thinking. Thank you for being a part of this community of curious minds who are striving to make sense of a universe that never stops surprising us. The sky is dark tonight. The moon is new. And somewhere out there, drawing ever closer with each passing minute, an ancient visitor from another star is preparing to say goodbye. Good night, everyone. Keep looking up. Disclaimer: this video contains a mix of scientific information, speculation, and theories that are not yet confirmed by mainstream scientific consensus. The views expressed regarding potential anomalies and alternative interpretations represent ongoing debates within the scientific community. Always consult official sources from NASA, ESA, and peer-reviewed scientific publications for verified information on 3 Atlas and other astronomical phenomena.